we ought to start with a little bit of your background. Mm-hmm. So what did you start researching, and then what are you researching now?
Okay. So I started out my research in mathematics in Austria, in Vienna, where I actually didn't look at image processing or imaging at all. I started out with so-called partial differential equations, which are equations of a function and its derivatives. So they can express change over time or space. And they are models for various natural phenomena in physics and biology. Lots of things are explained via these differential equations. And my first paper, again, had nothing to do with image processing. It was actually on the Canhillier equation, which is an equation that describes phase separation and coarsening in alloys, in metallic alloys, for instance. So when you cool them down to a certain temperature, you have a mixture of two. And if you cool them down to a certain temperature, they are starting to separate from each other and coarsen out and build these larger areas. And so there is an equation that models this kind of phenomenon, which is the Canhillier equation.
Okay.
And my first paper was on the stability analysis of a certain type of solutions to this Canhillier equation. Stability analysis meaning that if you perturb your initial condition a little bit, how much is your stationary solution, that is when you let time evolve infinitely.
Okay.
How, when a stationary state is a state where the system is in no change anymore. How much do these stationary states differ from each other when you just perturb the initial condition a little bit?
And this is in the context of creating alloys or building alloys for structures, or was there any particular purpose?
Well, the purpose is a lot with these differential equations to simulate certain phenomena. Mm-hmm. And so if you understand how stable these stationary states are, so if you are at a stationary state, and then you perturb the stationary state a little bit, is it going back to the same stationary state?
Okay.
Or is it going somewhere completely different? So you kind of understand how these systems react to perturbations that are naturally occurring because we are in real life and things happen.
Gotcha. Okay.
Yeah. So it's more an understanding of the physical processes involved in, mixture of alloys, for instance, or things like that.
And were you at a technical university where you would be focusing on alloys, or this was a personal interest?
Not at all. So it was just actually, a lot of applied mathematics on the continent, which is everything else in the UK, basically here in Europe, is applied mathematics very much means that what you're doing is inspired by applications, but eventually you end up with a mathematical problem. So it was really the driving factor was, we were interested in analyzing this equation, and there were techniques coming up that are kind of cool. And so it was just a kind of intellectual interest in this equation.
Okay.
That was the driving factor for this particular paper. But then, during writing this paper, researchers at UCLA, in particular the group of Andrea Bertozzi, used this same equation to do image restoration. And image restoration meaning you have a digital image and there are parts of this image which are damaged for some reason, or where you have objects which are occluding some other object of interest that you want to get rid of the occlusion or something like this. So you have one part in the image that you somehow want to replace by something that is suggested by the surrounding area of this region.
So is this similar to content-aware fill in Photoshop?
Exactly.
Okay.
Exactly.
Okay.
Yeah, exactly.
But this predates the Photoshop development, I assume.
It actually does. And I mean, also the content-aware fill is actually very much based on some of the things that have been initiated by people like Andrea Bertozzi. So, I mean, the technique is different in what Photoshop is using, but it's still based on research in mathematics, in fact.
Yeah.
It's a differential equation. Maybe if you wish, that is not the Canhillier equation, but is a different type of differential equation that is non-local. It's taking patches in images and kind of copy and pasting them into the region that you want to replace.
Yep.
But anyway, so she used the Canhillier equation to do that. And that was a kind of eye-opening moment. And then I moved into image processing, still sticking to differential equations at the time, and actually looking at image restoration. So at this Photoshop content-aware fill type problem. And that was basically my PhD. My PhD was about image restoration.
Okay.
And during my postdoc, then I moved more and more into what is called inverse imaging problems, where what you are observing or what you're measuring in the first place is not an image. Like when you take a photo, the digital image is an image. So, but there are certain applications, like in biomedical imaging, where what you're observing is not an image directly, but is some transform of this image, like in image tomography, for instance.
Okay.
Think about CT, for instance, computer tomography. What the tomograph is measuring, are projections of your three-dimensional object, which is whatever you have in your body. And from that, you want to reconstruct the object. So projections meaning in the CT sense, a particular sense, which is that you send X-rays through the body. And what you're measuring, so you're sending them through, what you're measuring at the other end is the attenuation that they feel when they travel through the body, depending on which type of tissues they hit. And so that's what you're measuring on the other hand. And you can model that by saying what you're measuring is a line, is an integral along the line that the X-ray takes through your body, where you're integrating over the attenuation that it feels.
Yep.
And so from that, and that is a very old problem, it goes back to radon. It's called the radon transform. What you're measuring is not an image, but it's the radon transform of your image, which are line integrals over the image density that you want to reconstruct. Right? That consists then where the density is different in different parts of your body, and then you can see organs in your body and stuff like that. Right.
And so the likelihood of there to be some amount of it missing that you need to fill or recreate or denoise is much higher than an image and less obvious.
That's quite obvious because, well, first of all, we are in a finite dimensional world. So, you don't have all possible infinitely many line integrals of your body measured.
Yeah.
And then it's not even, that would be still okay if you're measuring as many line integrals as you're corresponding to the resolution of the image that you then want to compute from these line integrals. But then very often it's not like that because you want a very high resolution image because you want to look at all the details in the body.
Right.
But, you don't want to, measure so many line integrals because you don't want to radiate the patient so much. You don't want to send tons of X-rays through the patient. So you have a lack of data. You don't have as much data as you want for a high resolution image to reconstruct. And then there is noise because these are measurements. Right. And there is always noise in measurements.
And so were you doing denoising work as well at the same time?
It's integrated in the reconstruction approach. So in the mathematical algorithm that reconstructs an image or the three-dimensional inside of your body from these line measurements, there is the denoising is integrated into this reconstruction step coming from these line integrals reconstructing a 3D.
Gotcha. 3D object. Okay. And so what I know about denoising mostly through audio, like a Fourier transform and that kind of thing. So how are you doing it with an image? How are you denoising in the algorithm?
So with images, it depends what you think is important in an image. That will determine how you're going to denoise it, let's say. A very successful assumption that has been made for designing image denoising approaches is and has been and still is that the most important information that visually guides you of what this image is showing you, but also that helps you if you later want to quantify something in the image, are the edges in the image. This is the most important thing. Where are boundaries between different objects?
Okay. Yep.
When you think about it, what really makes an impression on you of what this image shows are colors, and the boundary between these colors. Where are the colors changing? And these are the edges in the image.
Interesting.
And to preserve those and not make them blurry, blurred out is something that a lot of research in image denoising has gone into. So image denoising methods which can preserve edges in an image. And so the Fourier type techniques are good. They can smoothen out the noise by taking away the high frequencies.
Yeah.
But they will take away the high frequencies everywhere.
Right.
Which means they will also take away the high frequencies that correspond to edges where the image function is changing rapidly.
Yeah,
right?
so you're looking for the delta.
This is a very high frequency component of your image, but this is a component you would like to keep.
Yeah. Okay.
And so you want to differentiate between the high frequency components in the image, which are just noise, and the high frequency components which correspond to these very characteristic features that you want to keep.
Gotcha.
And so, there are various techniques, but one very successful one is total variation regularization, for instance, which is a technique that has been used a lot by people in image denoising to, that models this assumption that you have sharp discontinuities. Median filtering is a maybe simpler thing to understand, or that people might have heard about, which is not exactly total variation denoising, but it's related.
Gotcha.
So median filtering instead of Gaussian filtering, maybe, where Gaussian filtering corresponds to your Fourier taking away the high frequencies type of thing.
Oh, okay. Got you. It's so funny. When I was doing Photoshop with the Onion, we were always actually interested in blurring edges, because one of the most obvious things to spot a Photoshop is a sharp edge and a soft edge in the same photo. Okay. So for instance, like if I were to cut you out and then put you in front of the White House, if the photo has a slight blur, so like the depth of field in the photo is like, say, like a 1.4 aperture, which creates a very, very like shallow depth of field. So there's a lot of blur. Yeah. But if you're crispy, someone can immediately spot that you were dropped into the photo. So it was all about blurring the edges to trick someone into thinking that it was in the same photo.
Okay.
Okay. So in your context, these algorithms that will handle the edge sharpness, are they hand-coded, or are you using machine learning to create them? How does that work?
So they are classically hand-coded. And this is maybe something that is now, more and more being replaced by other things where image denoising nowadays, I think the best image denoising approaches are actually coming from deep neural networks.
Okay.
So, these handcrafted methods get more and more beaten in terms of performance by some of these neural network approaches. They get beaten in certain scenarios, though, because they get beaten on the type of examples they have seen already, or similar type of images that they have seen already, right? If you present them with something completely different, right? If you only train them on photographs of animals or whatever,
right?
And then you present them with a CT image or with a CT scan, they will not be able to handle that. So that is one of the things I think where still handcrafted models have a certain justification of existence in a sense, because there is still, although we can do GPU programming and everything, there is still not enough computational power to train a machine to know everything, to learn everything about the world.
Right.
And so I think while, in certain scenarios, if you know what you want to apply your image denoising approach
Well, it was like the ImageNet thing from like almost 10 years ago.
Exactly.
Yeah.
If you know that, then it's fine.
Right.
And that's good. But if you want, think about, for instance, one big thing in CT, let's say, or in different types of biomedical imaging, let's say MRI, magnetic resonance tomography. The type of image that you get, the resolution, the contrast and everything very much depends on how you do the acquisition. how many, let's say in the CT case, how many X-rays you have been shooting through the patient. But also, and that is actually connected to what I just said, also the type of scanner you're using. Are you using a GE or a Siemens or Toshiba or whatever? They have different settings, and they have different ways of going from the measurements to an image. And so, if you train an algorithm, for instance, a neural network on one of these scanners, it doesn't mean that it works on images of another scanner.
Really? So they're producing entirely different data. I thought they were just like basically the same tools inside with a different logo.
Well, so this is the other interesting thing. It's not entirely different, right? You might not spot also visually what the difference is. But this is one of the things that also people start, more and more hopefully start to, do some research and understanding this, that even small perturbances that are consistent.
Yeah.
In small differences that are consistent between the different scanners might contribute to your algorithm then failing. I don't know if you have seen these adversarial errors where you do a little perturbation and then all of a sudden it classifies the image into something completely different.
Right.
So, yeah. So I think the really very exciting and for mathematicians in particular, the exciting opportunity that neural networks are now offering, in contrast to these handcrafted models, are that they can go beyond just saying, I want an algorithm that preserves edges,
right?
Which is a very simplistic view of the world.
Yeah.
But on the other hand, that there are lots of unknowns in these algorithms. On the one hand, that mathematicians, I think, should be exploring and try to bring some of the analysis and some of the methodologies that help us to understand why these handcrafted models work, because we can prove properties about the denoising abilities of these methods, of how stable they are, for instance, to perturbations in the images. We know how that works, so we can prove things about them. We have error estimates and things like this. And to bring those over to neural networks, I think is very exciting. But for that, bringing some structure into these neural networks is also important. And that might, on the other hand, when you think about these neural networks having these 100 millions of parameters that are adapting themselves to the data, maybe in some cases it would be better to not have a million parameters, but have an intelligent structural way of reducing the search space.
Right.
And as such, bring some structure into the problem, which helps you make statements about stability and things like that.
Well, and also statements about what the algorithm is actually doing.
And what statements about what the algorithm is doing.
Yeah.
Because, so that is another thing, right? Because since when you look at these handcrafted models, you have started with a hypothesis, right? You have started with a hypothesis of edges are important in images.
Right.
And then you come up with a mathematical algorithm that is exactly doing what you want it to do, right?
Yeah.
Or, then you have to make sure that it's actually doing what you want it to do.
And if it doesn't, then that code is bad. Then it's not.
The code is bad, or your model is bad. Maybe you have to change your model in a certain way. Okay. But you understand why things are happening.
Yeah.
If you have millions of parameters and then, you train this algorithm to do something, and then you get a parameterization that is 1 million different parameters, how are you ever going to interpret that? There are ways, where machine learning people are trying to interpret classification results, for instance.
Yeah.
You have these salient features that you can detect in the image what was important for the classification to do this or this.
Yeah.
But it's still limited. Mm-hmm. And I think, there are lots of very, very cool opportunities.
And so are you guys working on hand stitching the two together at this point? Like what's the status of the current research?
Yeah. So there different people are trying to do different things. So, I can first tell you what I've been doing over the last couple of years. So the last couple of years, what I've been doing is I've been trying to, starting with these more handcrafted models, nothing to do yet with neural networks. I started with the handcrafted models, and then for certain parts in these models where I wasn't quite sure about, are edges really the only thing I'm looking for? For instance, I've tried to parameterize them in a certain way.
Okay.
But not with a million parameters, but maybe with 10 parameters or something like this. And then learn these parameters from actual examples that I would like my handcrafted model to spit out. Mm-hmm. And this is what we call bi-level optimization, or parameter estimation. I mean, people have been doing this for a long time, but now I think the motivation comes more from, there is a certain interpretation in terms of machine learning that is kind of exciting, that where people are, more interested in. So this is one way, and levels of parameterization vary in this context. But the good thing is you have a handcrafted model in the end that you still understand.
Right.
And that you can still prove things about. You still have guarantees on your solution. You have guarantees that if you don't have these adversarial errors, that if you perturb a little bit, you get a completely different result. This is really something you don't want.
Right.
The other thing is, and this is more blue sky, and this actually goes a little bit against what I said before, which is we have been starting to use deep neural networks for problems in computer tomography, for instance. And there at the moment, we cannot prove a lot of things. But we can see some ways of how to combine these more handcrafted models with neural networks in the sense of what you feed them with. For instance, the prior information you feed them with, the data, maybe not just the measurements, but maybe also the information that the measurements are actually line integrals of the 3D object that you want to reconstruct.
Yep.
And doing this in a kind of iterated fashion where you always go back to the fact that, actually remember neural network, these are line measurements that I'm feeding you with. Remember this. And then you do another sweep through the neural network.
But then how does that work in the context of building out a model around, say, like, I don't even know in an MRI how many images are created or like 10 or lines are monitored, but like, say you have 10,000 images. Mm-hmm. But you want to create a combination of a hand-coded algorithm and a machine learning system. Mm-hmm. Mm-hmm. How do you go about tagging all that stuff?
What do you mean exactly? How are you going to...
So what I understand you're saying is like you're giving it more data than just like the original source material.
Yes.
And so how do you do that with a more like at larger scale?
Computationally, you mean?
Yeah.
Okay. So, computationally, we are doing this in a sequential manner.
Okay.
So, we're not, so you can do it in different ways, but in a sequential manner means that you're not feeding it the 10,000 images at the same time, but you're doing it bit by bit. And you're adapting your objective towards this. Okay. Another thing about computational performance is also, of course, that the optimization that is underlying, but this is not just the problem that we have. This is a problem that, neural networks have in general, is that you do not necessarily need to solve your optimization problem you're training exactly. And maybe sometimes, or most of the time, you actually don't want to save it exactly, because you only have a finite amount of training examples. And so when you think about what these neural networks are doing, they're trying to minimize a loss over the training examples that you have. Mm-hmm. But this loss is only an approximation of many, 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 many more images that you want your neural network to work for. And so very often you do not want to solve that exactly. You don't want to minimize your loss exactly for this training set.
Okay.
And so there are different types of optimization methods that people are using, but the main thing in machine learning is stochastic optimization. So you don't minimize, exactly for all the variables that you have, but you randomly pick a certain amount in every sweep through the network that you're optimizing for, and then you randomly change which ones you're optimizing in the next sweep and so on.
And just so I understand, minimizing loss, why don't you want to do that?
So what you're minimizing, the loss, let's say, could be the least squares error.
Yeah.
Between let's go back to denoising. Let's say you want you want to train your neural network to optimally denoise images by saying, for this training set where I have both noisy and clean images,
Yep.
I want that if I sum over the difference between the denoised image, so you feed your neural network with a noisy image, it gives you a denoised image.
Mm-hmm.
You want that this denoised image is closest in a least square sense to the clean image that you know in this case, because you have a training set. You have a label, you have a true label for this noisy image, which the label in this case is your ground truth image.
Okay.
And you want your denoising method, which is this neural network, to produce denoised images such that all of them are, in the least square sense, closest to the original label, to the ground label, which is the clean image.
Okay.
And you want that to work over all the images in the training set.
Got you. Okay.
Okay, so, but let's say you have 10,000 of these images that you both know the clean and the noisy image. If you would perfectly fit to this training set, if you would perfectly minimize this loss function, you could think, and again, people are not really understanding this, and I also don't really understand this, but conceptually, the idea is what you actually want to minimize is not the loss just over the training set, but it's the loss over an infinite amount of images, which you then want to denoise.
Gotcha.
Right?
Okay.
But you don't have all these infinite amount of images. So why would you want to very accurately minimize the loss over this finite amount of images? Maybe you don't. Maybe you only approximately want such that you still have freedom.
Right.
Such that it could be optimal also for more images that you don't have.
So if you in other words, you could train it on the wrong thing, and it could only work for like denoising photos of apple trees.
Exactly.
And then then you're in the same place that you were in the beginning.
Yeah, exactly.
With the hand coded.
Yeah.
Okay, gotcha.
So the idea is, if you only do it approximately, you might be able to generalize it more.
Gotcha.
But all of this really, there are some attempts to understand this, but all of this is not really, so I'm hand waving here because I can't really say anything mathematically about that.
But have you pushed your research into practical applications at this point? Like, are you working with, companies or student groups or anyone else?
So my main collaborations are actually with people in academia, but from other disciplines. Mm-hmm. So we have been collaborating a lot in recent years with people in the hospital, in the university hospital in Cambridge. So with clinicians and medical physicists, different types of applications. One of the things I said before is that I got more and more interested in these problems where you don't measure an image directly, but only indirectly via these X-rays, for instance. So developing algorithms which can get the most out of very limited amount of data, the most out in terms of very high resolution images, is something we have been collaborating a lot with people in magnetic resonance tomography, in particular in the Addenbrooke's Hospital, which is the local Cambridge hospital here, but also with people in chemical engineering, where one of the driving factors for people in chemical engineering is, for instance, there is a group here, which is the Magnetic Resonance Research Center, where they look in particular at processes which are dynamic. So they have these tubes filled with water, and then they pump certain things through, and they want to understand what the dynamics of this process are. So now if you think about not just having a static 3D object, but having something that changes over time as well, and now thinking back about how many X-rays, not in magnetic resonance tomography, these are not X-rays, but just going back to an example what we had before. So, not sending through so many X-rays means you don't have a lot of data to reconstruct.
Right.
Which now, if you want to track something dynamically, also means you're not measuring a lot per time step. If you want to have a very high resolution over time, it means per timestamp, you can't acquire as much data as if you would have, if you just have 1 second for reconstructing your organ inside the body at this particular timestamp. And then the organ is moving again and you need to go to the next timestamp and so on. You have less data for reconstructing each timestamp as if you would have a static object and you would have 10 seconds to acquire this instead of 1 second. You can measure much more, right?
Right.
And then you reconstruct just one image. But now we have maybe want to reconstruct not just one image in 10 seconds, but 10 images because we want to see something evolving over time.
Right.
So here also the challenges are along these lines of getting high resolution out of limited data. Another thing which is not connected to indirect measurements so much than these applications in magnetic resonance tomography is that we have collaborations with people in plant sciences, for instance. So they are interested in monitoring forest health or forest constituencies, let's say, from airborne imaging data. So they fly. Mostly in my collaboration, they fly, so not so much satellite, but more flying. They fly over forest regions, and then they acquire different types of imaging data. They acquire just photographs, aerial photographs, hyperspectral imaging data or multispectral imaging data, which means you do not only have RGB, but you have a broader range, you cover a broader range over the light spectrum, so also the invisible light. So you don't have just 3 channels, but you have 200 channels or something like this in your image.
Yeah.
And hyperspectral imaging is interesting. So the spectral component that you get from these measurements gives you an idea of what the material properties are of these trees. So it tells you something about what.
Really?
Yeah. So this is so the spectral component tells you something about the material that you are looking at.
So in other words, like
so different materials have a different signature in the light spectrum of how they reflect light back. They have a different signature in the light spectrum.
Okay. And so the intent would be to figure out, say for instance, like an invasive tree that was taking over an area. They could figure that out by flying right over it. Gotcha. Okay.
And then the other thing, so this is one, and then or 2 aerial photographs and hyperspectral imaging. And then the third thing that they are often acquiring are LiDAR measurements.
Yep.
Where you do not just get kind of a planar picture of the trees, but you actually get a 3D model of the trees.
Yeah.
So this is also nice. Yeah.
I was just watching a documentary about that, about searching for Mayan runes with LiDAR. Flying over the Yucatan Peninsula or something. Essentially like saying like, hey, we could take 20 years for an archaeologist to like dig around in the dirt, or we could just fly over it and look for the hard stuff and see what happens. Yeah. Very interesting. And are people also looking to this in the context of, for instance, like denoising like camera footage from anything, like security on one hand?
Yeah, I haven't done so much work in that myself, but there are, of course, CCTV cameras are everywhere.
Yeah. I mean, it's kind of the terrifying output of figuring out this research, right? Like being tracked everywhere, like in the UK in particular. Like I imagine people are looking to do this, right?
It's quite funny because when you think about these crime TV shows, CSI, whatever, Miami or whatever, there are always these funny things, right? So you have a very pixelated image, and you press a magic button, and then you can zoom in, and then all of a sudden you can see everything. So. When you think, so this is ridiculous, yeah? Of course, you can't do that, but you can't do it now. Maybe, if you have all these machine learning methods, which have learned to look at just pixels and then know what is a very probable match in terms of high resolution, maybe at some point you can do it. But then you don't know if you're right or wrong, right? Yeah.
Just by chance, I was reading a New Yorker article from, I think, 2010 about this guy in Montreal, allegedly finding 500-year-old fingerprints using different kinds of like spectral photography.
Okay, cool. I haven't heard about that.
Oh, okay.
But tell me more about it.
So I don't want to give away the whole thing, but and then there was an ensuing lawsuit actually from him to the New Yorker, saying it was libel. But basically what happens is he was accused of faking these fingerprints that may or may not have existed.
Oh man, okay.
Yeah, and copying them from a real one, duplicating them onto the back, using proprietary methods to find them out. But you are interested in doing it whether or not it's legit. You want to work with
I
art
hope so.
in this.
I mean, I'm going to tell people that it's fake.
Yeah.
Yes.
Okay.
Yeah, that's the whole idea.
Yeah. Is it what direction are you going with art?
So it kind of in Cambridge okay, let me say a bit more. So when during my PhD in Vienna, there was a collaboration that we had with physical conservators, so with conservators who were looking at particular wall frescoes, in an old apartment in the city center of Vienna, which are called the Neidhardt frescoes. I'm not going more into detail, but they were in the process of restorating these frescoes. And so that was my first-hand experience there. And there, the idea was that, it takes them a long time to physically restore these wall paintings. And once you have restored it, there is no way back, right? You need to decide what to do.
Yeah.
Because then it sticks. And so our idea was to help them by creating a virtual template of how the restoration could look if they do this or this or this.
Right. Yeah. So because the important part is a fresco is actually part of the wall chemically. It's not paint.
Exactly.
Yeah.
Exactly. But even with paintings, if you do something, if you manually really, if you physically restore them,
yeah,
you've done it.
Yeah.
I mean, you can still maybe, try to go back, but I mean, you're just, you're changing a historical piece
right
of the world, right? So I mean, this is yeah. Anyway, so coming here to Cambridge, I got to know people in the Fitzwilliam Museum, which is a museum here in Cambridge, and they're interested in illuminated manuscripts. So I met a very good colleague of mine who is the keeper of manuscripts in the Fitzwilliam Museum. Got interested in this idea of virtual restoration because illuminated manuscripts are so fragile that the culture is you never physically restore them. You never physically restore them. They, if they get damaged or altered over time, you leave it.
Wow. Okay.
You leave them like this. And so the idea was, couldn't we create a virtual restoration and, kind of exhibit the original manuscript and the virtual restoration next to each other? And so last year there was an exhibition in the Fitzwilliam Museum, which was called Color. Mm-hmm. And in this exhibition we had one piece which was a page of an illuminated manuscript, which had been altered over time, actually manually overpainted.
Okay.
And what we did was that we exhibited the manuscript and next to it the virtual restoration where we took off the overpaint. And and that has led to other things. But I mean, this is kind of the idea that you don't physically change something, but you virtually do it, which is, nothing damaged. You just virtually create a digital copy of this manuscript and you play around with it.
So you're not only going back in time to see maybe restoring it to its original, vitality, its original color, but you're actually going deeper into the layers. This has been painted over.
Yeah.
And so you can go further in with imaging and then you kind of apply everything you might already.
Yeah.
Wow. That's super cool.
Yeah.
So if someone's really excited about this kind of research, if they want to get into it, what would you point them to? Where should they get started?
Depends what their background is.
Okay, yeah. So they have they have a CS degree. They're interested in imaging. So they're technical, but they haven't done anything in particular in this field.
Okay, so what I would advise is to look. So I think in particular, when you think about the US, I think some of the cool things that came out of image processing in the last couple of years were from UCLA. So if you look at some of the applied math faculty there and some of the online lecture material or, YouTube videos of some of their talks, I think that would be a good source to look at. Very classical names are Stan Osher, Andrea Bertozzi I mentioned, Malik, Perona, Stefano Soato. There are lots of people. There is, now the name escapes me. I can tell you a few more things afterwards, but I think just to look for mathematical approaches to image processing, I think it would be the first thing I would do. There are very good introductory books to look at that explain a bit of the basics.
Great.
But yeah, I would first start reading a little bit in these more general foundational books. And then I think just starting from that, you immediately go to the, more modern recent years research. I think that would be a good way to start.
I can catch up to you, maybe.
Yeah, maybe.
Or apply here.
Yeah.
Awesome. Well, thank you so much. Thanks for making time.
Yeah, thanks.